Okay, in this talk we are talking about active covering, which is a version of active learning. Okay, let me start from basics. In a
This one is louder, so it's more convenient for you.
Yeah, it's louder. Okay. Okay, let me start from the basics. In a machine learning task, we are trying to learn a pattern from some label data, right? So we have the whole data set at hand and everything is labeled, and the larger the database, the better. So if we have the computational power to do the computation, we just want larger and larger data sets. We don't care about the any cost. There's no cost in collecting the data, right? And we don't care if the value of one example is more than another example in the data set, because we can look just at all of them, right? We can think of how we can, in the learning process, some of them may have more effect than the others, and that we can detect during the learning phase. But at the beginning, we don't care. We just put them, feed them all to the learning model that we have. But this is not the reality. This is not always the reality. Sometimes the data comes at a cost, right? So for example, we are labeling the data using a crowdsourcing, right? We have a lot of examples, but we don't know the actual labels. We give these to human and pay them to label them, right? We show them an ad and ask, does this ad looks offensive or not? And we pay for each label. Or another example is when when the data is generated by running experiments, right? For example, we give one drug to a patient and we wait to observe the result, right? So we're maybe paying the patient, maybe we are paying for the drug, and it's not just more drug better, more experiments better experiments. We need to know which patient is a better candidate to try the drug on. Or which data is a more variable data to label using crowdsourcing. Another example is sometimes we have a limited amount of data that we can gather, right? We are not paying for these examples, but for example, when we show a search result to a customer, we may ask, does this search look relevant to your query or not? Right, but we don't want to keep doing this always. Or maybe we can ask a user if this email is actually a spam or not, but we don't want to keep doing this for every single email. So we have a bound, we have a limited number of queries that we can make, and this is because we don't want to bother the user by much. So this falls in the context of active learning. There is a cost or limit on the number of examples that we can label, and we want to take that into consideration. Active covering is a sort of an extreme version of active learning. In active covering, we want to find all the positive examples, right? For example, in credit card fraud, we care a lot about finding all the positive examples. We prefer to find all the positive examples. We don't mind if we query, we still have a bounded number of queries that we can make. Maybe if we see some transaction, we can call the customer or text the customer and ask if this is an actual transaction or not. But we want to go to the extremes. We don't want to have a 50%, 80%, 90% success rate. Or for example, so in credit card fraud, we don't want to keep bothering the customers, but we want to stop all the frauds, and we want to learn the signs of the fraud along the way. Maybe a new fraud comes in, and we want to learn this along the way, right? There is a similar concept in testing. For example, when the COVID pandemic just started, we didn't know the actual symptoms of the COVID, right? We knew something, but we couldn't categorize it perfectly. And actually, in different regions, there were different signs. We couldn't from the signs, we couldn't say very perfectly if this person has a COVID or not. Maybe by now that we have many tests, we can detect COVID patients much better than before, right? So again, at the beginning of COVID pandemic, the tests were very worthy, maybe not very expensive, but very worthy. We didn't have too much tests. We didn't want to waste tests. We wanted to find we prefer to find all positive patients, right? And we were trying to learn the symptoms along the way, right? So this is in active covering. The only theoretical difference is that we want to find all the positive examples, and another the theoretical difference that happens here is that in active learning we just want to learn the model, so we don't care if we are querying 50%, 10% positive, 90% negative. But here we have some exploitation, right? It's like bandits. Along the way, we are collecting rewards. We are not just learning, we are collecting the rewards as well. When we test someone, we learn about symptoms, and we also collect the reward. We also realize if this person has COVID or not. So there are some theoretical differences here. So let me formulate the problem. We have, again, these are basics. We have a space of examples. So this is one example is one feature vector, like all the characteristics that we know. And we can represent this as a point in a high dimensional space. So for example, symptoms of a patient is one feature vector. It's like one point in a high dimensional space. Maybe we can look at an embedding of the features. So we have the features, we throw it in the neural net, and maybe look at the first layer and use that as one point in a high dimensional space. So each example is one point in a high dimensional space, and we don't know the label of each point. We can query the label of the point, and it's positive or negative, right? So in active covering, we just have positives and negatives. So this is one example. We have each of these positive and negatives each represent one example in a two-dimensional space. We don't know if they are positive or negative, but they are. Okay, I will go through a previous work and our results. Our paper is math heavy. I'm not going to go through any math, but I'm trying to give you at least an intuition. Okay. What we want to do is we want to do something better than looking at everything, right? If there is just one positive here and everything else over there, we cannot easily detect this, right? Or if maybe positives are here and then there is one positive here, we cannot detect it, right? So we need to have some assumptions, right? Although if there are very few points that are further away and the rest respect our assumption, we will just miss those small ones and find the rest. And this is expectable. We cannot find the outliers without querying everyone. So these are the assumptions of the previous work. We have milder assumptions. I will go through those as well. The first one is that we have finite number of positive components. What's a positive component? Look at the support of these positive examples. We don't know the support, but we just have the assumption on the support. Look at the support of these positive examples. They're finite connected component. We don't want it to get infinite. I'm not saying it's limited. I'm not saying it's small. It's just finite. Okay. Again, I said if there is one small positive here, we cannot find it, right? Or if there are many negatives and very shallow area of positives on top of it, we cannot find it without querying all the negative ones, right? So the other thing, the other requirements that we need to have, at least actually the previous work had to have, is that the support of these positives are not very narrow, and wherever there is positive examples, it's not very shallow, right? The probability of, when there is a probability of seeing a positive example, this probability is not very, very small, right? We can have 0, but if it's not 0, it shouldn't be too small. and the negatives don't get too dense, right? So if there is some positive here, there is a lot of negative here, we may accidentally go to these negatives and query a lot of them. So they don't want to have too many negatives. These assumptions make sense, but some of them may not be necessary, right? For example, if we add like a few dimensions to our space, add like 1-2 independent dimensions to our space, the density of the whole space is going to decrease, right? The whole space is going to get shallow, but the problem is not getting harder. If you realize that these vectors are independent, these new dimensions are independent. So some of these assumptions are not necessary. We are going to try to remove those assumptions, and by removing those assumptions, we are removing some parameters from our reglet, our final cost. Okay, let me go through the previous algorithm, which actually makes sense. It looks very natural. At the beginning, we don't know anything, so we do a random sample. We sample some of the points and query them. These red ones are the ones that we randomly sampled at the beginning, right? And then some of them are negative. We don't care about them. Some of them are positive. We go look around those positive ones. So there are 3 positives here. We go around them and look around them. And we continue doing this until we see enough positive examples. So I said we go around them and look at the examples around them. There are two algorithms, 2 ways to do this. The first one is that for each of them, like just look at these first initial samples and find the nearest unsampled example to these and query that. The other way to do that is that if you find another positive, then take that into account as well. If you find something that's very close to that one, go query that, right? So there are two algorithms to find. One of them is just pick the next nearest neighbors to the initial positive samples that you have. This is the first one. The second one is pick the next unsampled nearest neighbor to all the positives that you found so far, right? Okay. And actually the second one works better than the first one because it's more adaptive, but it's not always easy to implement that because querying, maybe when we query something, it takes time until we observe the result. Okay, so how do we measure the regret? How do we measure the cost that we are paying? If you look at the support of the positive examples, we sort of have to query everything in that support, right? Because the whole thing that we know is this geometry. So inside this support, we don't know anything. All of them looks the same to us. So if we know the support of the positive examples, we have to query all of them. So that's the minimum that we are going to pay. Anything more we pay is the excess cost. So excess cost is anything outside the support of the positive examples. We don't know the support of the positive examples, so if we knew, we could just find the optimum solution. We don't know that, so but we need to bound the cost of that. Okay, what we do is that we think of this. If say this is the whole example that we have. We have something here, the exact same thing is here, but like spread it further through the space, right? These two shouldn't be different. We shouldn't be, like intuitively shouldn't treat these two differently, right? So if we sample like 1 point from this and 1 point from this, the time that we said that the distance, the time that from here we get to here is equivalent to the time that we get from here to here. So the time that we so the time that we get from here to here would be equivalent to the time that we get from here to here, but this isn't the right thing that we should do, right? The right thing is to scale this by the density, right? Otherwise, like when like say these two are the initial samples, when we are querying this, we are querying these as well. And we will end up querying all these negatives while we are querying these positives, right? So the thing that we do is that we scale it by this factor. This is the density square root d of the density. And this is going to be equivalent to, think of these examples as a fog. The distance is going to be how hard is it to walk through this fog. So with this, we are going to have asymptotically the same query cost, the same cost as the previous work, but we have some better parameters. So the assumptions that we need are slightly milder. Finite number of positive components we still need. But for positives, we just need the positive not to get too narrow and too shallow at the same time. So it can be shallow and big, or narrow and dense, but it shouldn't be shallow and narrow at the same time, because it's like just having one bad example. And the density shouldn't change very rapidly. Otherwise, this factor doesn't mean anything when you go a little further. So these are the experiments that we do. Like in all of these experiments, the pink one is our algorithm. It's in all of them, it's the best. In this one, you see the top line is pink, but it's not the best one. There is a green line roughly exactly at the same location, which is better. So this is the AUC. The AUC this is our proposed algorithm. The second one is where we are not optimum, but by like 0.2%. And for the rest, our algorithm is the best. Okay.